Hello, everyone. It's 10:20. Welcome back. Bruno?
Yes, yeah. Just a second.
Bruno has been a maintainer for a long time and is an important contributor to the Einstein Toolkit and to hydrodynamics research. He hosted a great Einstein Toolkit workshop in Trento some years ago, but you're now in, oh shoot. My mind is blanking.
Milan.
Milan, yes, sorry.
No problem.
Anyway, he's here this morning to talk to us about Spritz. It's a new DRM-HD code, and Bruno, take it away.
Can you see the slides?
Yes, I can.
Okay, perfect. Okay, yeah. So first of all, Spritz is the name actually of an alcoholic beverage that is very popular in the north of Italy. And it's also one of my favorite drinks. So the code is named after a drink. You have a picture here on the left. So this work is done in collaboration with Riccardo Ciolfi at the National Institute for Astrophysics in Padova, Federico Cipolletta, who is currently a postdoc at Rochester, even if actually is working from Italy because of COVID. And then Edoardo Giangrandi and Beatrice Giudici, two master students that are in my group here in Milan. And they are both looking actually for PhD position. They are going to finish their master pretty soon, by the end of the summer, more or less. And so they are looking for PhD position. And then we have Jay Kalinani, a PhD student at the University of Padova, working with Riccardo Ciolfi. And then Lorenzo Sala, he was a master student in my group. And so this work started also thanks to him, but now he's doing a PhD on different stuff. He's working in the LISA group in Trento. Okay. So Spritz is a GRM-HD code. So here I have a slide with some possible application for general relativistic and magnetoaerodynamics. And all these results are chosen because they were all using the Einstein Toolkit. So for example, here at the bottom, you have some supernova simulations with magnetic fields that were done by Philip Most and collaborators in 2014. And these use the GRHydro code. Here you have a simulation run in 2D. So in axis symmetry, essentially, you see a beautiful jet. Then you run the same simulation in 3D, and you see that life gets much more complicated, and the jet is not so much axis symmetric. Then on the top right, you have a simulation from the group in Illinois using the original Illinois GRM-HD code for a neutron star black hole merger. Then here at the center, you have a paper from my group. The first author was Takumu Kawamura, who was a PhD student at the University of Trento. And it is a simulation of binary neutron star merger with magnetic field. So here you see the different phases of the evolution during the merger of the neutron star system, in which you see the formation of a torus here in light blue, and a funnel, low density funnel in yellow, and here there is the magnetic field lines. So this is the kind of structure that, for example, can give rise to short gamma ray bursts. And here on the left, you have another simulation. These are bigger scales. This is a simulation of an accretion disk around a supermassive binary black hole merger. And this was also, I think, done with the original Illinois GRM-HD code. There is a paper by Gold and collaborators published in 2014, which you see essentially matter accreting on the two supermassive black holes, and you have this sort of two dancing jets produced by each of the black holes. So each of these simulations benefited from the Einstein Toolkit. Some of these used codes that are completely public inside the Einstein Toolkit. Some others, like this one, for example, the one by Kawamura et al. 2016, instead used the many routines from the Einstein Toolkit, but then a private code that was written by me over the years. So the set of equations you need to solve are the following ones. Frank already mentioned briefly this. So you have the Einstein equations, G mu equal 8 pi T mu, using a system of units such that the gravitational constant is equal to 1 and the speed of light is set to 1. Then this equation gives you essentially the evolution of the metric given the energy momentum tensor. Then you need the equation that drives the evolution of matter. So you have the hydrodynamic equation, so the conservation of energy and momentum, the fourth divergence of T mu nu equal to 0, and the conservation of baryon matter, so the fourth divergence of J mu equal to 0, where J mu is just rho, the rest mass density, multiplied by the force velocity of the fluid. Plus an equation of state that relates the pressure to the rest mass density, the specific internal energy or the temperature, and possibly other variables, as I will discuss later. And this is the energy momentum tensor that we typically use in this kind of simulations. We assume a perfect fluid, no viscosity, and moreover, we assume what is called the ideal MHD limit, which means that we assume infinite conductivity. The different terms in this tensor are just the rest mass density, rho, the specific relativistic enthalpy H, B squared is the magnetic energy density, U again is the force velocity, P is the pressure of the gas, G mu nu is the four-dimensional metric. And then of course you need also the evolution equation for the magnetic field. If you are in the ideal MHD limit, where as I said, you assume that the conductivity is infinite, which is a good approximation for the interior or neutron stars, then you need to solve just half of the Maxwell equation. In particular, you just need to consider the fourth divergence of the dual of the Faraday tensor equal to 0. These are essentially corresponds to the Maxwell equation for the curl of the electric field, which the curl of the electric field is equal minus the derivative of the magnetic field with respect to time. And so this is the equation that gives you the evolution of the magnetic field. And then from this, you also get the constraint equation on the magnetic field. So the divergence of B equal to 0. So these are the equations you need to solve if you want to study magnetized fluid in general relativity. In order to study, for example, as I showed in the picture before, the formation, for example, of jets in the case of neutron star black hole mergers, or for example, the formation of jets or an accretion disk onto supermassive black holes, or even some supernova explosions. These are just some examples. Now, in order to solve this equation, you rewrite them in a conservative form, which means essentially you reduce a set of equations in a system of equations in which you have a derivative with respect to time of a conservative set of variables, which is usually indicated with U, plus the divergences of some fluxes that will be defined later, equal to a source term. Now, the original Valencia formulation provided a way to rewrite in a conservative form only the equation of hydrodynamics. Then once as also to add the equation for MHD. As I said, told you there is one equation which is the derivative with respect to time of the magnetic field equal the curl of the electric field. And the electric field in ideal MHD, it's related to the velocity and the magnetic field itself. And you have the divergence of B equal to 0. In 2006, Anton et al. Were able to rewrite also this in a set of flux conservative equations. So the set of equations you evolve for all variables are written this way. So the derivative with respect to time of a conserved variable plus the divergence of a flux equal a source term. The conserved variables are defined by this set of variables. I'm not going to go into details. I will share the slides, so you will also get this equation, or you can refer to papers that I'm going to cite later. But essentially, if you want, this is the conserved density. This could be seen as the conserved momentum. This could be seen as the conserved energy, and is just the magnetic field. And then you have terms for the fluxes and the source, which are just defined in this slide. So these are the terms for the fluxes for the different conserved variables, and these are the source terms, which essentially depends only on gravity. So if you are in a special relativity, this source term goes to 0. Now, if you evolve those equations and you start with initial data in which the divergence of B of the magnetic field is 0, then analytically, the divergence of B will stay 0 all the time. The problem is that when you solve these equations numerically, because of the approximation you introduce by solving those equations numerically, like the truncation error, you may introduce error in the divergence of B. So the divergence of B may start to differ from 0, which means that you start to introduce monopole in your solution, and therefore you may create also instabilities. Over the years, a number of methods have been introduced in order to keep the magnetic field divergenceless. The first and oldest one is the constraint transport scheme, originally introduced by Yi in 1966. Then another method that has been more recently developed by then collaborators in 2002 is what is called hyperbolic divergence cleaning. And the third method is called the vector potential evolution with the modified Lorentz gauge. It was introduced by Tien et al. 2012, and the modified Lorentz gauge was also introduced in the paper by Faris et al. 2012. These are three different schemes that can be used to evolve the magnetic field. So in the case of constrained transport, there is in particular an approach, which is called the flux city approach by Balsara and Spicer 1999, in which essentially they realized that when you rewrite your GRMHD equation in a flux conservative approach, you can find a relation between the electric fields and the fluxes of the magnetic field components. And these are the relations that are posted on the right. So what you want to do is to evolve the magnetic field, for example, the phase of this cell. This is the X component located at position 1i plus 1 alpha JK. And to evolve this, you have that dB in the t, so the derivative of the magnetic field with respect to time, is equal minus the curl of the electric field. So you want to take the curl of the electric fields along the boundary of this phase. To compute the electric fields on each of these edges, what you can do in a flux conservative approach is just to use this relation and interpolate the fluxes across the phrases that shares the same edge. So for example, if you want to compute the electric field on this edge, you just interpolate the fluxes as written here at the bottom across this cell. This will be the Z component of the flux for the X component of the magnetic field. Then you have the Z component of flux across this phase. This is the I plus 1 JK plus 1 half. And then you do the same for the other phases. So this will be the X component of the flux, and then again the X component of the flux here. So it's the expression here given at the bottom. More details about this can be found in the original paper by Balsara and Spicer in 1991, or you can also go and have a look at the paper that I wrote in 2007 with Luciano Rizzola, from which this figure was taken. If you do this, you can automatically satisfy the conservation of the divergence of B. The problem with this scheme that it's incredibly complicated to implement this scheme in adaptive mesh refinement. So it works very well without any problem in Unigrid, but if you start to use mesh refinement, like for example, with using Carpet, the driver that Eric Schnetter mentioned yesterday, this is incredibly complicated because as Eric mentioned, you have some interpolation that you need to do when going from cursor to final grid, and this interpolation may introduce error in the divergence of B. There are some schemes that allow to rewrite these interpolations method in order to guarantee the conservation of the divergence of B, so to guarantee that the divergence of B stays 0, but they are incredibly complicated to be implemented, and they are not at the moment available inside the Einstein toolkit. So the first code that I wrote for GRMHD was called Whiskey MHD. It made the use of the Einstein toolkit. It has been used over the years for several simulations of binary neutron-star mergers and also for one simulation of accretion to supermassive binary black hole mergers. If you go on my webpage, brunogiacomazzo.org, you can find a link to all the papers where the code has been used. It supported a very simple equation of state, like ideal fluid equation of state or piecewise polytropic equation of state, which are good approximation of cold equation of state, but not advanced enough to take into account the microphysics that is really relevant for the post-merger evolution of binary neutron-star system, where you want to have a more accurate description of what's going on. In particular, if you're interested in studying the possible electromagnetic emission coming from this object. Whiskey MHD initially implemented a fluxity approach that I described it to you, but since this fluxity approach cannot work with adaptive mesh refinement in the current version of Carpet and Whiskey MHD, we decided to switch to another method, which is the other method that I listed before, and essentially is to use a vector potential. So instead of evolving the magnetic field, we evolve the vector potential, and then we compute the magnetic field from the vector potential. So in each edge, in principle, you would like to have the vector potential here and evolve it according to the electric field. Again, in the past, Carpet didn't provide prolongation and restriction operator for variables that were staggered, which means variables, for example, are not located in the center of the cell. So in Whiskey MHD, what we did was instead of evolving the vector potential on the edges, was to evolve the vector potential at the center. And this required to change the way the electric field was computed. We still use an interpolation of the fluxes, but the expression is different. This is cited in Giacomazzo et al. 2011. So this is something that works with adaptive mesh refinement, but is not good enough, as we'll discuss in a moment. Other codes that are available and that we consider in order to improve the realism of our simulation is GRHydro, the code that was mentioned before by Frank. It was originally based on the public version of the WSGI code, but it has been since that time developed completely independently. It's a quite advanced code. In particular, it supports also tabulated equation of state via an equation of state driver, which is called Yosemite. And this allows you to use very advanced equation of state in order to study with a greater level of realism what happens during the merger of magnetic system. The problem with GRHydro, at least from my point of view, and that when evolving with the magnetic field, it doesn't provide, in my opinion, a very robust way to treat the magnetic fields with mesh refinement. If you want, I can comment on this later. So these options were not a good option for me if I wanted to move to more realistic simulation. So it added on the plus side, the possibility to have a realistic equation of state, but I don't consider this code too robust from the point of view of magnetic field mesh refinement. Another code that is available in the public is Illinois GRMHD, developed by Carietti and collaborators. This has a very robust mechanism to evolve the magnetic field. It uses the vector potential, but it's in a staggered formulation. So the vector potential is really located on the edges, and I will comment in a moment why this is important. The only problem that when we started developing Spritz, Illinois GMHD did support only ideal fluid equation of state. Only recently they included support, for example, for tabulated equation of state. So we decided to develop this new code, Spritz, in which we wanted essentially to import all the best aspects that we had in WSGI MHD, in Illinois GRMHD, and GRHydro. Essentially, we want one code that was able to handle as accurate as possible the magnetic field evolution using a staggered vector potential formulation like the one used in Illinois GRMHD. But we also wanted to be able to use advanced equation of state, including finite time per tabulated equation of state via, for example, the Yosemite driver that is used by GRHydro. And on top of it, we want also to be able to have a neutrino transport, to consider the effect of neutrino radiation on the post-merger evolution of the binary neutron star system. And for this, we decided to use the publicly available Zelmani leak torn. So first of all, why staggered vector potential? This is a figure that you can find the paper we published this year. First author is Federico Cipolletta, in which we compare the results for a shock tube test. It's a Riemann problem. It's actually the Balsara 1 problem for those that are more interested in details. And we show the evolution, essentially the final results of the y component magnetic field, By, as a function of x. During this problem, you have the formation of shocks and rarefactions. And in red, you have the solution evolved with a staggered magnetic field approach, in which means that the vector potential is located on the edges of the cell. And in blue, instead, a centered approach for the vector potential, which means the vector potential is located in the center. And essentially, you see that when you don't use the staggered approach, you introduce some post-hoc oscillations. These are not an instabilities, but they are quite annoying, and they can be removed by adding a crystallograph dissipation. But if you use a staggered approach, like the one that is now used in Spritz and is also used in Illinois GRMHD, you really get a very smooth profile after a shock. There is no formation of these oscillations. Spritz has been tested with a standard battery of tests, so 1D test like the Balsara shock tube problems. In 2D, we use the cylindrical explosion, the magnetic rotor, and the loop advection. These are all tests that were also done by GRHydro, so we compared also the two codes in order to show a very good agreement. And then in 3D, we did the spherical explosion test that has been done probably by no code, I think, using Cartesian coordinates. So we have one, probably the few GR code that did this test in full 3D in Cartesian coordinate. And then as usual, the evolution of a stable neutron star, non-rotating neutron star, a TOV. And this is an example for one of these tests, for one of these TOV. This is a magnetized TOV. In this case, it was using a simple ideal fluid equation of state. I will show you in a second the results instead with tabulated equation of state and neutrinos. But in this case, you have here the initial data on the XZ plane. This solid line represents more or less the surface of neutron star, and color shows the intensity of the magnetic field, and the white lines are the magnetic field lines. And on the right, you see the evolution in time of the maximum direct mass density normalized to initial values, and the maximum of the magnetic field. And here there's different resolution. The red line is a very low resolution. If I remember correctly, it was solving the neutron star with the 16 points per neutron star radius. So it was incredibly low resolution and very dissipative. So you see that the density goes down as well as the magnetic field. As you increase the resolution, the rest mass density starts to oscillate closer and closer to initial value, and also the magnetic field gets better conserved. We are recently working on new tests of the code, in particular for what concerns neutrinos. As I told you, the Spritz used the Zelmani leak code, which is publicly available on stellarcollapse.org, and is mainly described in this new paper by O'Connor et al. 2010 and Otto collaborator 2012. It implements a very simple leakage scheme with a gray approximation, which means you don't account for different energy of different neutrinos, and you only account for 3 neutrino species: electron neutrinos, anti-electron neutrinos, and all the other neutrinos that go together in what I call nu X. You also need to add an evolution equation, which we did for electron fractions. We need also to modify the conservative primitive scheme, and for this we use the one that is described in the paper by Valenzuela collaborating in 2015. And for the initial data, since I'm not aware of a TOV solver inside the Einstein toolkit that can generate initial data with tabulated equation of state, we generate our initial data with Lorraine using tabulated equation of state. And to generate initial data, usually you have to choose if you want, for example, a cold neutron star. For example, you can fix the temperature of the neutron star to a very low value. For example, you want a cold neutron star, so you set the temperature to be fixed to 0.01 MeV, for example. Then you need also to make another assumption, and in this case we assume beta equilibrium, which is a reasonable assumption for a star that is in equilibrium. And after you have done that, you reduce essentially an equation of state in which the pressure dependent on the rest mass density, temperature, and electron fraction, to another equation of state that depends only on density. And with that done, you can then solve the TO equation. For the evolution, instead, you use the full tabulated equation of state. So you let the temperature, the entropy, and so on to evolve, as well as the electron fraction. These are all the tests that we are currently carrying on. This is part of a paper that we are preparing and that we are going to submit hopefully later this summer or before the end of the year. All the tests use the Latin expressed 220 equation of state. The equation of state can be found at stellarcollapse.org. It uses adaptive mesh refinement with 5 refinement levels, and the finest grid, which is the one that covers the neutron star, has a resolution 0.12 in cactus units. This corresponds to approximately 180 meters. So some of the tests include also runs with Gerhydro in order to compare Spritz with Gerhydro. Some of these are just without the neutrino leakage, so just testing, for example, the evolution with the tabulated equation of state but without neutrinos, and others instead also include the evolution of neutrino. And then some of the tests also include magnetic fields. In particular, we included tests with the magnetic field of the order 10 to the 16 Gauss, so a sort of magnetar. These are some results, since I think I'm running out of time. These are tests without the neutrino emission. So on the left, you have evolution again on the maximum of the rest mass density, normalized to its initial value. For different tests, these are initial data in which we assume the entropy to be uniform across to the initial configuration. And these are tests. I'm not going to describe the different lines because they overlap over each other very well, but essentially one test was run with Gerhydro, the other 3 tests were run with Spritz, and one of those will also run with magnetic fields. And essentially they overlap on each other very well, perfectly. The star is perfectly stable and oscillates around its initial equilibrium configuration. On the right, you have evolution of the maximum, the temperature, normalized by the initial value. And also here you see that essentially the maximum temperature stays more or less constant. There is a bit of drift, but nothing serious. And this instead is a test with neutrino emission. On the left again, you have the evolution of the maximum of the rest mass density normalized to its initial value. And again, these are tests with Gerhydro, with Spritz, and also with Spritz with magnetic field. And from the point of view of the rest mass density, they overlap very well on top of each other. And the evolution is really stable. On the right, instead, you have the luminosity in the different neutrino species. These are luminosity for the electron neutrinos. This is the luminosity for the other kind of neutrinos, tau and muon neutrinos. And this on the bottom is the luminosity for the anti-electron neutrinos. What is interesting at the top, if we focus on the electron neutrino luminosity, And there are some small differences between Spritz and Gerardo. Spritz is the blue curve, Gerardo is the red. So there's slightly difference in the neutrino luminosity. But there are also some difference between Spritz without magnetic field, the blue line, and Spritz with magnetic field, which is this dotted yellow line that you probably cannot see very well, but this is where the mouse is located. So the magnetic field, since it maybe affects a bit, maybe the evolution of the surface of the neutron star by adding an extra pressure, and this could explain, for example, this small difference in neutrino luminosity. Other things that we also implemented in the code, and this is thanks to Beatrice Giudici, so one of my masters in Milano, is to implement also higher order method. Spritz is indeed like Whiskey MHD used initially implemented only PPM, which is a third order reconstruction scheme, but we decided to implement also higher order scheme. In particular, we went for Winod Z, which is considered to be one of the best schemes to simulate binary neutron star simulations and to compute gravitation with Sigma. And this, you can find some reference about it in Bernuzzi and Dritti 2016. And what we did, we implemented this reconstruction scheme with an higher order finite difference scheme to compute the fluxes, in particular fourth order and the sixth order scheme, the ones that are called HLE4 and HLE6 here. And we did a test with a very simple solution. It's called the simple wave test. It's a solution that is an equation in which, initial data in this case are a simple wave, which is initially very smooth and then later produce a shock. But while it's smooth, you can check the order convention in your code, and you see that you use Winod Z, which is a fifth order reconstruction method, together with HLE6, which is a sixth order derivative scheme, finite difference scheme for the flux, you really get fifth order convergence. Then it goes down because, as I say, the solution produces a shock, and then the convergence goes down to 1. The next steps will be to test this scheme also with a single TOV evolution, like those we showed before, and then also with a full binary neutron star merger. So to conclude, Spritz is a new code. It's publicly available. The version that we described in Cipollette et al. 2020, the paper we published at the beginning of this year, which does not include neutrino support, is already available on Zenodo. We will also make publicly available the new version, which also includes neutrino support once we finish to write the paper and the paper get published, of course. So Spritz works with magnetic field, finite temper tabulated equation of state, and also neutrino emission. So I think it includes some of the most relevant aspects to simulate binary neutron star mergers. As I said, we are finishing testing, in particular, the scheme for the neutrino emission, as well as the inclusion of high order methods. And as I said before, Edoardo Giangrandi and Beatrice Giudici, these two master students worked with us in the development of this code. In particular, Edoardo Giangrandi is helping with the testing neutrino emission, while Beatrice Giudici is the one that helped with the work and including the high order methods. Are both going to finish their master by the end of this year, so they're both looking for PhD positions in case you're interested. And I think my time is really over, so if you have any questions, I cannot see the chat.
All right, I am looking for questions either in chat or in or people with raised hands. I see Frank Loeffler has raised his hand. Frank, you want to ask your question?
You mentioned you have a first version of the code publicly available on Zenodo. Does that mean you won't push updates there? Because I guess Zenodo is essentially you put it there and it stays like it is there. Do you have a repository or something people can use?
No, at the moment there is not an open source repository, a public repository, sorry. So on Zenodo, we are going to upload the versions that are used for each of the papers. So on the version you have on Zenodo, which is version 1.0.0, is the one used for Cipollette et al. 2020. Once we are going to finish the test for neutrino and we get a new paper published, we will post the new version, which will be probably called 1.1 of Spritz, and that will go on Zenodo. In the future, once we start using Spritz also for binary neutron star simulation, so we are really sure that the codes work perfectly, my plan is to push for this code, for the inclusion of this code into the Einstein toolkit. So in that case, we will probably make the current Bitbucket repository, which is private, we will make that publicly available. But at the moment, we are just releasing a single version that we really trust. We don't have a public Bitbucket repository at the moment.
Yeah, I guess you trust the version that you used for the 2020 publication because you used it for a publication, right?
Yes.
Okay.
All right.
That version, anyway, that version includes anyway the finite temperature tabulated equation of state. It just does not include the neutron emission.
Is there a license on it?
I don't remember which license. I mean, it's a, okay, I don't remember if I put like a specific license, probably yes, but I mean, it's you can use it. You can download the code on the node. I don't remember which license we used.
Okay, thanks. Anyway.
Sorry about that.
Next question, we have Amitesh.
Hi, Bruno. Actually, there was just a quick question. Can you hear me?
Yes.
Yeah, actually, I was asking about the slide in which you showed neutrino rest mass densities. Can you just take us back to the slide?
Sorry, which one?
Yeah, this one, yeah. So
okay.
In the earlier stage, as we can see the left graph, in the earlier stage, can you account for the deviations from the normal pulse behavior as can be seen in the later stages? Can you account for these differences, in the starting stage?
Sorry, I didn't understand very well the question. Can you repeat?
I mean, in this initial phase, we see these lines are a little bit more wobbly than the after stage.
Okay. Well, this is because, I mean, the TOV is a spherically symmetric solution. You're putting this solution on a Cartesian grid. And so essentially you are giving to this solution a sort of a small kick. You're perturbing that a bit. So at the beginning you have the larger amplitude. Then you also have some numerical viscosity, even if here is pretty small because we use a quite good resolution. And so this big jump at the beginning is simply if you want this spherical star that is put on a Cartesian grid and get this sort of initial perturbation, start to oscillate, and then it starts to oscillate less and less because of numerical viscosity.
Oh, okay. Yeah, I get it. Thank you.
Okay, the next question we have is from Eric Schnetter.
Hello, good morning. I have a question regarding the magnetic field evolution. Are you adding some dissipation even if you use the flux CT method?
Okay, so
you had a graph where you showed the oscillations if you don't stagger things and no oscillations otherwise.
This, no, okay. If I use the staggered approach, so the red one, no, I don't use any dissipation.
Okay, thank you.
All right, next question comes from a mad scientist.
Okay.
Hey, good evening, everyone. Can you all hear me?
Yes.
Yes.
So I was just curious about, do we have some form of benchmarking to see how fast is Spritz as compared to other simulations for solving the similar problems?
Oh, to be honest, no, I didn't perform that test already. So I cannot answer this question. I should be similar in speed, I think, to Geragro or to WhiskyMHD. I don't know about the Illinois GMHD because maybe that was a bit more optimized. But I didn't do a comparison. That actually is a very good question. It's something that we should do. We focus more on the physics than on the performance, but it's a good question.
Thank you.
Okay, I see no more hands raised. Let's see, is there anything else in the chat? I do not see any more questions in the chat. So virtual applause for Bruno.
Thank you all.
Thank you.